Greetings and good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our thermodynamic lectures. Today we want to look at forced flow boiling. In our last lecture, we had discussed about pool boiling and we saw several aspects of them. So today we want to look at forced flow boiling. Forced flow boiling differs specifically from pool boiling, especially given that in pool boiling, we say that we had this vapor blanket which resulted in burnout. But in this forced flow boiling, we are going to see that that's not the same situation. We basically have what we call dry out, but then burnout is possible in certain sections of the forced flow boiling. Now, in this forced flow boiling, we have a once-through condenser tube. What does that mean? We have a once-through condenser tube. This once-through condenser tube is simply a straight flow system where whatever we have, when we are vaporizing our fluid, when we reach the exit, it is not recirculated. It is not recirculated. So this once through condenser tube will be in a vertical position. And why is that so? Because remember, in the forced boiling system, we'll have a two-phase system. We'll have both liquid and vapor. We'll have both liquid and vapor. And if we were to use an horizontal tube, then there will be no symmetrical flow in that particular system. So the vertical position is a much more easier and simpler position to account for than if you're dealing with a horizontal tube and you're having a two-phase system. Now, in this once-through tube, which is held in the vertical position, we are going to have our liquid, which is at or below a saturation temperature, enter at the bottom. And then when it enters at the bottom, then of course we have a constant heat flux in the system. We're having a constant heat flux in the system, and of course it will go through the heating processes which we are going to describe shortly. So we're saying this once-through condenser tube is a straight flow system where the exiting vapor is not recirculated. So we don't have recirculation there. So we have just said that in this vertical tube, so let's just note that the position, when we have a vertical, once through condenser tube, we will have, like we have said, the entry of the fluid of the liquid at the bottom. And this liquid can be at a saturated temperature or slightly below. So when a vertical once-through condenser tube has been assembled, we allow entry of the liquid at or below its saturation temperature to enter at the bottom of the system. of the unit. Now, like we have said, it is a two-phase process. We have liquid and vapor. And so this is very, very important. The volumetric ratios of the liquid and vapor are very, very important in this particular system. And secondly, their velocities are very important in determining the type of flow regime which you are going to have. Very important to note that this is a two-phase system. We have a liquid and we have a vapor. And the volumetric ratios of the liquid and vapor are very important. And in addition, their velocities will influence or will affect the flow regimes in the system. So let's just note that. So in this system, we have a two-phase. We have two-phase. That is liquid and vapor. And their volumetric ratio is critical in determining the nature of flow regime. Also, the flow velocity is critical in determination of the transitions. Determination of the transition between the various flow regimes. So this is a two-phase. Like we have said, this is a two-phase process, a two-phase system where we have liquid and we also have vapor. We have liquid and we also have vapor. And we are saying that their volumetric ratio is very, very critical in determining the kind of flow regime. And not only that, the flow velocity is also very important in determining the transition between these flow regimes. What do we mean by this, by flow regimes? We can identify a few flow regimes, a few obvious flow regimes in this particular system. And that does not mean that we don't have intermediates of these main flow regimes, which I'm going to cite. The type of flow regimes. Flow regimes. One, when we have a lot of liquid, when the liquid is in large quantities, then what we are going to have is a situation where we are going to have the vapors dispersed in that liquid, and that we call the bubble flow. So we have vapor. And here the liquid, you see, is in greater quantity, and so the vapor will be dispersed in the liquid, and that we call the bubble flow. The other type of flow regime is where we have bigger vapors. It's like the smaller vapors have coalesced. So this is vapor. And this is referred to as slug flow. And of course, the relative amount of liquid in the case of flag flow vis-a-vis that of bubble flow, the liquid amounts are diminishing because we are heating up this quantity. Remember, we said that we have a constant heat flux in the system. Just note that. We have a constant heat flux in the system. The other regime, flow regime, will be the so-called annular flow. And in the annular flow, we have a thin film of liquid at the walls. Thin film at the walls. So both are both liquid. And this is a thin film of liquid at the wall. So let's just call it thin film of liquid at the wall. This is the annular flow. And finally, of course, as the heating has taken toll on the liquid, we now have more, we are approaching the vapor completely. So we have the mist flow. So we have the mist flow. So I repeat, we have the flow regimes, and the flow regimes are determined by the volumetric ratios of the liquid and the vapor. In other words, we have the two phases which are in this system. And secondly, the flow velocity is also very important in determining these transitions between these flow regimes. And always remember, like we mentioned, that the heat flux is constant in the system. The heat flux is constant in the system, not on the walls, not on the walls of the tube, but in the system. And you are going to see why I've emphasized that, not on the walls. Now, let us just now look at what would be a practical case now. Now that we have an idea about the flow regimes, what affects it, let's now try to look at a real situation. Let's now have a look at a real situation and have our system. Let's draw a system and try to describe what will happen in practice. That will not necessarily be like a hard and fast rule, no. But whatever description we are giving is closer to what you will find empirically. So let's look at the empirical flow pattern. The empirical pattern in a vertical tube. Approximate empirical pattern in a vertical tube. So let's have our vertical tube. We are going to have it in segments. So one of the things is, like we have mentioned, we have the entry of our fluid. In this case, when I'm talking of fluid, I mean both vapor and liquid. But in this particular case, at this entry point, we are talking of the liquid, which we said can be at or below its saturation temperature. That is the fluid, so just note at or below its saturation temperature. Is at or below its saturation temperature. So let us just compartmentalize this vertical tube. Let's give it sections for ease of discussion. Let's call this section A. And of course, we say that we have a constant heat flux. Yes, not. So we have a constant heat flux, Q. That's a symbol you are now familiar with. We have a constant heat flux. So at A, we can say that there's not much boiling. There is no boiling. We can comfortably say that in this section, there's no boiling. And so basically we have free convection. So there's no boiling. So in section A, we have no boiling. Vertical conduction is by free convection. So we have free convection. Now, as the heating picks up, we are forming more and more vapor, and this vapor, like we have already said, is dispersed in the liquid. And so we have kind of the bubble flow regime. So we have vapor dispersed in the liquid. Let's call that section B. So we have vapor. We have now vapor dispersed in the liquid. We have already said that's the bubble flow. That's the bubble flow. And as we continue heating, we are forming more and more of vapor. We are forming more and more of vapor at the walls. Section C, we are forming more vapor. We are forming more vapor at the walls. At the walls. Wall. And now we are going to reach so we are graduating systematically into the slag flow system. So here we have bigger vapor. In the bigger vapor, coalescence of vapor into bigger units. And as we continue heating, remember we have already seen the bubble flow in our system, and now we have also seen the slag flow in our system as the vapors coalesce more and more. And so in this particular system, so let's have this as a discontinuation. Let's just have that. So that as a discontinuation, let's call this D, so that we draw another one here. So we have already said more vapor in section B. In section B, we are forming more vapor. More vapor. On continued heating, more vapor is formed. And they coalesce, graduating into slag flow, graduating into slag flow. So here we had the bubble flow. Here we have the bubble flow. Here we now have our slag flow. And of course, on continued heating, we will graduate into the annular flow now. And remember, we want to join. Let's have the continuation. We have cut. It's like we have cut our tube and we're joining it up here. So remember, we are in section D. So here we are continuing in section E here. We have the annular flow regime. We have the annular flow regime, and of course we have a thin layer. We have a layer of liquid. As you already said, we have a layer of liquid. A thin film. Layer of liquid at the wall. Let's call it E. Let's call it E. So this is just a continuation of that quantity there. So we have our thin film, and so this one, the regime is the annular flow. Now, as you continue heating, this thin film, this layer will continue thinning out. It will continue thinning out, becoming thinner and thinner as you continue heating. And we transition into more vapor, This wall layer, this layer of liquid will thin out. And now that is going to create some problems that as you continue heating. So let's write in section E, we have the annular flow regime. On continued heating, the film of liquid at the wall thins out. It thins out until finally it is completely discarded. It's no longer there when it thins out. And what does that mean? There will be a sudden change in temperature because of the non-wettability of the wall. The wall is no longer wet, so there will be a sudden rise in temperature, and that is what we call dry out. Very important to note that. When we are in the annular flow regime, as you continue heating, the film on the wall, that film will continue being depleted. And then when it's completely depleted so that the wall is no longer wet, the wall is no longer wet, we are going to have a sudden rise in temperature. Remember, just think, when we talked about pool boiling, when we reached a certain critical heat flux and there was a vapor boundary, vapor layer developed. If you look at our lectures, and I continue urging you humbly to try and look at those lectures so that we build up things systematically, there was a sudden increase in temperature, very big increase in temperature. Here in this particular case, the wall is no longer, the wettability of the wall is zero, and so there will be a sudden increase in temperature, and this we refer to as dry out. On complete thinning out of the film, there will be a sudden increase in temperature. Process referred to as dry out. Dry out. Sudden increase in temperature, that's dry out, due to non-wettability of the wall. Now, this is a very dangerous case when you now have dry out, because there can be tube failure. There can be tube failure. So even in designs, it's very important to note that when one is designing, one has to take into account, you must be able to predict the occurrence and as precisely as possible the occurrence of the dry out, because you can have tube failure and that can be very serious. So we are saying that we can have tube failure. Very important to note that. So dry out can lead to tube failure. This can have very serious consequences. If, for example, you are dealing with the boiling water nuclear reactor, that can be a very serious consequence. So one needs to know, be able to predict precisely the possibility of the system undergoing dry out. And now, remember we said that in the system we have a constant heat flux. If, for example, the temperature at the wall is what's made is made constant, then you will avoid this kind of problem. But if you have the constant heat flux in the system, then that's a possibility. Dry out is a possibility, and that can lead to tube failure. And that's very risky, for example, when you're dealing with boiling water nuclear reactors. This can be a challenge in the case of boiling water nuclear reactors. And not only that, it's not only the dry out which can lead to tube failure, which is a serious threat for a system such as a boiling water nuclear reactor. You must also remember that in this particular type of system, the volumetric ratios of the liquid and vapor is critical, because that will determine the absorption of neutrons in that system. In addition, for the nuclear reactor, volumetric ratio of liquid and vapor is critical in the absorption of neutrons. The absorption of neutrons. It's very critical. Just remind yourself the simple atom picture. Remember, simple atom picture, as an atom, we had in the nucleus, we had neutrons and protons, and we had electrons circling around that nucleus. So the neutrons are particles in the nucleus. So it's the nucleus, the neutron, and the protons. Those are particles in the nucleus. And of course, circulating around is the electrons. And the electrostatic forces are in play here, determining various aspects of very many things in terms of the reactions of these atoms and so forth. And so what we are saying that the ratio, the volumetric ratio of liquid and vapor is critical in the absorption of neutrons. And so when you're dealing with the boiling water nuclear reactors, you want to be very, very careful in terms of predicting if at all this dry out. So you should not want that to be there. And we have said that you can maintain a constant temperature on the wall other than having a constant heat flux through the system. And then you're talking about that ratio affecting the absorption of neutrons. So these are very critical things. These are very, very critical things which one needs to know. And of course, finally, we have the superheated vapor. So let's just call that F. We have our exit. Finally, we have the superheated vapor. Exit the system. And like we have said, these are once through condenser tube. So we are not going to recycle the superheated vapor. We are not going to recycle it back again into the system. So this is a straight flow. That is a straight flow. And also remember that the non-wettability of the wall, which results in this sudden temperature rise, is partly as a result of the very poor heat transfer coefficient, now resulting as a result of that non-wettability of the wall. The heat transfer coefficient now is very poor when the wall is no longer wet, because the thin film is completely vaporized. And so we have that dramatic change in temperature, which actually brings in